A rigid body is a system of particles with a finite size that do not get deformed under the influence of any external force. The distance between any two particles of an ideal rigid body does not change even when it is under the influence of external forces. Let us now observe a bicycle in motion. If A and B are two particles on the frame, as the bicycle moves, the displacement is the same for both A and B. It implies that the velocity of particle A is equal to the velocity of particle B. This is also true with all other particles of the rigid body. Such a motion of a rigid body in which the velocity of all the constituent particles is the same at any instant of time is known as translational motion. Let us consider another rigid body, a door. Mark 2 points P and Q on the door and observe their motions as the door is opened or closed. When the door is in motion, do the 2 points P and Q have the same displacement? Their displacements are not equal. Hence, the motion of the door is not translational. This is known as rotational motion of a rigid body. The door is fixed to a line passing through the hinges. This fixed line about which a rigid body rotates is called the axis of rotation. When a rigid body is in rotational motion, how do the different particles on it move? When a rigid body is in rotational motion, every point on it moves along a circular path with the center on the axis of rotation, and the plane of this circle perpendicular to the axis of rotation. The rotating blades of a fan, the steering wheel of a car, and the Earth's rotation are some examples of rigid bodies in pure rotational motion. In all these examples, the axis of rotation is fixed and the rigid body rotates about it. Now, watch a spinning top. How does the motion of the top differ from that of the rotating bodies shown earlier? Here, the top is rotating about an axis. This axis of rotation of the top is not fixed, but rotates about a vertical line passing through its point of contact with the ground. This rotating axis forms an inverted cone, and this type of motion is known as precession. Even the motion of a grinding stone is of this nature. The axis of the grinding stone rotates about a vertical line that is normal to the base of the lower part of the grinding stone. In these examples, even though the axis of rotation is not fixed, the point of contact of the body with the ground is fixed. Observe the motion of the rolling wheel of a bicycle. The motion of any rolling body is a combination of rotational and translational motions. If a rigid body is fixed to an axis or a point, its motion is pure rotational motion. If the rigid body is free, it can have pure translational motion, or a combination of translational and rotational motion.
Let us consider a system of n particles with masses m1, m2, mi, mn, and the positions of these particles represented by x1, y1, z1, x2, y2, z2, xi, yi, zi, xn, yn, zn. The center of mass of a given system of n particles is a point in space. If the center of mass C is represented by the coordinates x, y and z, then x is equal to sigma mi xi by sigma mi, which is equal to sigma mi xi by m. Equation 1. Y is equal to sigma mi yi by sigma mi, which is equal to sigma mi yi by m. Equation 2. Z is equal to sigma mi zi by sigma mi, which is equal to sigma mi zi by m. Let this be equation 3, where m is equal to sigma mi is the total mass of the system. The location of the center of a mass of a system of particles depends on the locations of constituent particles and their masses. For example, consider two identical particles, each of mass 2 kg, located at points P of 2, 0, 0 and Q of 8, 0, 0. Since both particles are along the x-axis, even their center of mass lies on the x-axis. X is equal to sigma mi xi by m, equal to m1 x1 plus m2 x2 by m1 plus m2, which is equal to 2 into 2 plus 2 into 8 by 2 plus 2, equal to 5. The location of the center of mass is C1, 5, 0, 0. Note that when masses of both particles are equal, x is a simple average of x1 and x2. What happens to the center of mass if the mass of the second particle is increased to 6 kg? x2 is equal to m1 x1 plus m2 x2 by m1 plus m2, which is equal to 2 into 2 plus 6 into 8 by 2 plus 6, equal to 6.5. The center of mass C2, 6.5, 0, 0, moves closer to the heavier mass. If we place one more particle of mass 4 kg at point R, 6.5, 6, 0, where will the center of mass of the three-particle system be positioned? The given set of particles are on the xy plane, and hence the center of mass also lies on the xy plane. On simplification as shown, we get x is equal to 6.5 and y is equal to 2. The position of the center of mass is C3, 6.5, 2, 0. On observing the above cases, we can regard the center of mass of a system of particles as the mass weighted average location of the constituent particles. In vector notation, the position of the center of mass of a given system of particles is given by R is equal to sigma mi Ri by m, where Ri is equal to xi into I plus yi into j plus zi into k is the position vector of the ith particle, and R is equal to xi plus yj plus zk is the position vector of the center of mass. If we take the center of mass as the origin of our frame of reference, then sigma mi into Ri is equal to 0. Here, the sum is a vector addition. This equation can be split into three equations. Sigma mi xi into I is equal to 0. Sigma mi yi into j is equal to 0. And sigma mi zi into k is equal to 0. In the two-particle example discussed earlier, with masses 2 kg and 6 kg, if the center of mass is chosen as origin, then x1 is equal to minus 4.5 and x2 is equal to 1.5. Sigma mi xi